Okay, guys, here goes. Remind me if we get this correct here. I'm going to do it in black. If we start here at 1 for cosine, remember, then bring it down to 0. Drops down to a -1 here. Pi, 0, back up to 1. And I think I just grabbed one cycle, which looks something like this. Is that true? Now, I'd like to graph on the same grid, with your help, cosecant. Not cosecant, secant. I did cosecant last week. Let me choose another color here, guys. Graph it in reds. I'd like to graph f of x is equal to secant x. Now, I know secant's definition is 1 over x on that given circle. Which means these two are reciprocals. Now, help me out. You just stick with my graph here. If I start out with 1 for a value for cosine to begin with, I ask you, what's the reciprocal of 1? Which can be thought of as 1 over 1. If I flip it over to form a reciprocal, what's the reciprocal of 1?
Negative.
Not opposite. Reciprocal. Just stays right where it is. So guys, this is going to be the first point I'll deal with. When I reach pi over 2, my graph is at 0. So now I'm asking for the reciprocal of 0, and you can think of 0 as looking like this if you wish. I'm asking for a comma there, flip it over and form its reciprocal. What happens? It's undefined. That means on my grid here, I got to show right here is an undefined asymptote, vertical asymptote. When I move out to pi, I see on my cosine graph I'm down at -1. -1's reciprocal, guys, you'll find that to be a -1, so it's going to stay right where it is. 3 pi over 2 is unusual, that's 270 degrees. I'm at 0 right now. Reciprocal of 0, guys, would be what again? Undefined? Is that true?
Yes.
So we have another undefined here. Another vertical asymptote. And my graph goes out to 2 pi, and I know that 2 pi and back up to 1. On the cosine graph, reciprocal stays 1, so I'm here. Now the red ones, if you make out where the red ones are. I start here. This is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. Okay, I want to tell me the best I can do based on what you see right now. What's going on? What little piece of the graph do you see? I'll do it in red here. In quadrant 1. I've got this point to work with. What do you think the shape looks like in that quadrant 1 from 0 to pi over 2? You think it's going up like this? Now, quadrant 2, here. Okay, you think it's down here? And follows that asymptote and finally comes over and I guess picks that up. Do we agree? Okay. Now, I'm here. Now I'm in quadrant 3, which is right here, between 180 and 270. What do you think is happening in quadrant 3, this little space, to get my graph? Next piece of the graph.
Down.
That's, do you think it's going to go up like this? If you're saying down like this?
Down.
Yeah, should be wrong better than this, but it's like that. So you think there's a little piece down there doing that. When I go to quadrant 4, between 270 and 360, I don't think I have much choice here. What you see, that looks something like that. Do we agree at this point? Now, when I give you a handout of all the graphs, I'm going to give you a handout of all 6 graphs, and they have on this handout the domain, range, and some information about each graph for a little reference for you guys. If you look at secant, I don't quite have what they consider a full cycle. This looks pretty good here. Looks sort of like a parabola opening down, but it's not a true parabola. It takes that shape. I need to extend my graph. Now guys, I could extend it either out here to the left, maybe go out to a -pi/2, and finish this and get a full cycle, or I could go out to the right. I I think I'll move mine out to the right if you guys don't mind. Anyone tell me, what would be the next point after two pi if I need to extend a grid?
It's gonna be missed because it's same as pi over two.
Yeah, but what's its name? What do you think it is? I think I heard someone say it. Pi over two. Pi over two. And I think you are spacing by pi over two, aren't you, all the way through? Spacing by 90. And what should be happening at pi over two that's given to me? Looks like, based on what I see up here, there might be another asymptote. Put it in real quickly here. And then it looks like this piece that I'm lacking here, which we call a little bit, may look something like this. I think you guys will agree. And this graph should be more symmetric than the top graph. Make it a little bit more symmetric. And something like that. So guys, we got these, they should be more symmetric. Those two pieces though. Now they consider that the full graph. That's a parent graph for C. You could have done yours on the left, if you wish. Now if I accept this, you'll say, Professor, how about this little piece here? It exists, you really don't need it, if we accept this as your parent graph. Okay, so this guy here does exist, but if you don't want to use it, you'll have to use it. Now, based on this, right here,
The same.
yeah, I'm gonna list the domain, the range, any amplitude involved here, period, and so forth. Now, let's get the domain out of the way first, and I think I'll be very careful here. Looks like we have some asymptotes. I see one at pi over 2, 3 pi over 2, 5 pi over 2. Anyone tell me, how can I write the domain to show you cannot let x be those because it's undefined?
Pi plus pi and a half.
Tell me again. Pi plus,
Pi k or two.
okay, hang on, I'll test what you said. Pi over 2 plus pi k?
Yes.
I've heard that. Hang on. Now, there's, I think your textbook uses a k. Some textbooks will use an n. It's up to you. Where k must be an element of, you saw that symbol last week, of the integers. Nice numbers to be put in. If he's correct, we just choose right quick 0. That's an integer. If I replace in his formula k by 0, of course, that term drops out and leaves me pi over 2. Was there sure enough an asymptote at pi over 2? If I should replace k by 1, another integer, this becomes pi. Pi plus pi over 2, would that be 3 pi over 2? Which, was there an asymptote? He's got it. Thank you. There's your formula for the domain on the C graph. X cannot be those. Now, if he's correct, we're not going to test it though, but if he's correct, I could replace k by 50. And do it, and it looks like 50 pi plus pi over 2, guys, help me out. Is that 101? I did quick. 101 over 2? Pi? Is it 101 over 2 pi? Can you imagine? We're guaranteed way out here, there's going to be an asymptote. And his formula tells me it is. So this tells me where all the asymptotes are. Range, and by the way, you got to know all this. The domain range and all these. Range on this, not too bad. The up and down. I see negative infinity up to
-1.
absolutely. Wow. Let's put a bracket there. And tell me the other piece.
From 1 to.
Wow. Nice. I wish I could grade you guys just on your responses in class. All kinds of A's. Domain range, period. Just about as P. Guys, P in this case, the period, the point at which, if I wish, I could draw another cycle. Where is it that I could actually pick up and draw another cycle, and let's see what happens. And by the way, keep in mind the way I've drawn mine here, mine has been shifted over some. Does anyone have an idea before I show you how I would find the period just based on the graph? Your textbook, I think, even gives you formulas to find the period. Does anyone think they know what the period for the secant graph might be? What?
Same as domain.
No, same as domain. No.
2 pi.
I heard, say it again.
2 pi is-
Now, I heard 2 pi. Joseph, mathematician over there, tell me, why'd you say 2 pi?
Because it goes from pi over 2, if it starts at pi over 2.
And the ends at?
5 pi over 2, it's like,
How much distance is that?
that's 2 pi.
Exactly. I started here at pi over 2, and you could have started somewhere else, but I started at pi over 2, and he's 100% correct. I stopped at what, 5 pi over 2? So that distance, I stopped at 5 pi over 2, started at pi over 2. How much distance was covered? 4 pi over 2, or what? 2 pi. Joseph, students, that tells me, hang on just 1 second, that first asymptote was at pi over 2. Is that true? If I add the period number, that period is what makes things repeat. I've got pi over 2. Suppose I add to it 2 pi, the period number. Asymptote at pi over 2, and for some reason I decide to add to it the period number 2 pi, which should make things repeat. Common denominator and so forth, is that 5 pi over 2? Put together. Asymptote here, I added the period, so it should repeat. Did it sure enough repeat at 5 pi over 2? Yes or no? So let's try something else. At pi, it's down at -1. When should that happen again? My period says it should happen after I travel. This is pi now, guys. Pi in the red, right here. And I'm going to add to it that period number, 2 pi. And of course, we end up with 3 pi. Am I guaranteed out here at 3 pi, I think this is what, 2.5 pi? Is this 2.5, 5 pi over 2? So if I should move out again, do you think I'll be down here again over here? Will it repeat? You think it will? Okay. So that period number tells you where things are repeating. So if you find another asymptote, you're going to find another one, add the period to it. Or, as my student was giving me here, all this beautiful information, you may just know this information and know how to deal with it. Okay, guys. But that's the way the secant graph looks. At least one cycle. I can go off many other cycles. Okay? Any questions here? I don't think I'm finished up yet. Oh, amplitude. What would someone tell me from last week? Anything about amplitude on this graph?
From 1 to minus.
Let me get it.
From 1 to minus 1.
Oh, no. Okay, let me describe what amplitude was last week. It's the highest that the graph goes up from its axis. Look at this one. Here's the axis. X-axis. What's the highest that my red graph secant goes? And I'll identify that number, when you give it to me, as the amplitude.
There's no.
There is none. Yeah, it keeps on going forever, and infinity's not a number, they want a number, so we'll put none. So amplitude, period, domain, range, it looks absolutely beautiful. Oh, before I leave it, since you're going to be moved into calculus, let's do this. Let's find the limit as x is approaching, I'll just put it like this. As x is approaching, let's say 3 pi over 2. We're like calculus now. Of this function, which is secant. Secant in here. Look how fancy that looks. Okay, you're approaching 3 pi over 2. I see 3 pi over 2 right here. There's an asymptote, right, at 3 pi over 2. If I say approaching, you'll probably say, Professor, I see the graph, the red graph is approaching on the left. It's getting close to that asymptote here on the left. Also, it stays close to the asymptote on the other side to the right. So which side would you like for me to approach from? And that's where they use a superscript. If they use a superscript of a negative sign, they want you to approach from the left. So stay on the left of an asymptote and describe for me what the graph is doing. Guys, if I stay on the left, because 3 pi over 2, this is the left over here, left-hand side, what is my red graph doing the closer I get to that asymptote? It's dropping down through what? Is it going through negative infinity? That's the answer we want. Yeah, these markers are so nice, you need to bring more to me. You can bring a spring. Okay, limit, as x is approaching 3, 5, or 2, now let's use a superscript of a positive sign. Secant graph. Now I'm approaching the same asymptote, 3, 5, or 2, but this time stay on the right-hand side of it. That's what that positive sign says. Guys, the piece that's to the right of, but close to, 3, 5, or 2, the asymptote, is this little piece. You guys agree? And the closer you get to 3, 5, or 2, how would you describe the behavior of that graph? Is it going up forever the closer you get to that asymptote? So this time the limit is positive infinity. Guarantee you walk into a Math 7 class and they start with that. And I know what some of these instructors may start with the first week when you meet them. At least you guys have seen this. Okay? Guys, any concerns here? Now, the last one I'll graph for you. I've already graphed sine, cosine. Now cosecant, secant. This would be 6 of these. We'll graph tangent. The one I'm leaving out is cotangent. I will leave that up to you. So, letter B. I will see what this looks like, and I will stop. And X. And I gotta keep in mind what the definition was. It is this of the unit circle. And guys, this is one I think would be wise to reflect back to the unit circle and take that unit circle into a grid. This. And have it to do this for me. Let me put my critical points down here. All this is from the unit circle. Now I can draw the unit circle on the side here and refer to it and get to this grid. I think my students know the unit circle by now, but just in case. We know 0 radians, 0.10. Pi over 2, which is 90 degrees up here, point that. This is pi, point, negative 1, 0. This is 3 pi over 2, 0, negative 1. And the complete revolution, I could call this also 2 pi. Okay, those are just points that came from that unit circle. Now what am I looking at? I'm looking at y over x. Each one of these. If I start at 0, right here, and I place this order here, if I place y over x at 0, what would I end up with? Which is 0? Would I end up with 0 over 1? Is that y over x? That means my graph at 0 is at 0 for a value. When I reach pi over 2, something unusual happens. I'm doing this. That's the definition of tangent. I'm placing y over x. What happens if I place y over x up there? It's undefined. You're placing 1 over 0. So there's an asymptote right here. Vertical asymptote on the graph. When I go out to pi, which is here, I'm placing y over x. I'll be placing 0 over a negative 1. No problem. That's 0. At 3 pi over 2, down here, if I try y over x, I'm placing negative 1 over 0. There is a problem. It's undefined. And if I finish up the unit circle altogether, go all the way back over to 2 pi, back here, of course I get 0 again. So, Professor, where's the graph? Just connect those 3 points. Just draw a straight line, connect those 3 points, and I have the graph of tangent. No, you know that. Quadrant 1, from here to here. Please describe for me any angle that's in quadrant 1, this quadrant here. Any angle. Now you're replacing y over x, where you know from middle school, that's a positive situation. You place a positive over a positive, what do you guarantee you're gonna get each time? A positive answer?
Yes.
Which means my graph there in quadrant 1, since that's always gonna be a positive, should be above the x-axis. Now, I have no choice. I mean, in that quadrant 1, it's got to look like that. Stay above the x-axis and follow the asymptote. Next quadrant is quadrant 2, between 90 and 180. If you're in quadrant 2, middle school says you have this. And I'm placing y over x into a tangent, so I'm placing a positive over a negative, which gives me a negative, so that says right here in this quadrant, I had better be below. I have no choice. Below the x-axis to represent negative and follow the asymptote. Quadrant 3 is right here, and quadrant 3 for middle school tells me the point should be, I'll squeeze it in right here, guys, both coordinates are negative. So you're placing a negative over a negative, which turns into a positive. So here, this little piece here should have a graph what, above, and therefore it connects and does something like that. And we'll go all the way out to the next quadrant, quadrant 4, which is right here. Middle school, of course, tells us this. You place y over x in quadrant 4, you get a negative, which tells me that the next piece should be below in quadrant 4. Guys agree? Makes sense the way we described it? Now, just so happens, we lucked out here. Now, let me ask first though, can anyone tell me if I should want to extend my graph, these graphs go, the cycles go on forever. Can anyone tell me after 2 pi, you guys told me earlier, what would be the next point to this as a critical number if I wish to go out?
What oil?
5 pi over 2. And what do you think is happening at 5 pi over 2? Is there another asymptote?
Yes.
If there is, an asymptote, I would think then this is going to do this there. Anyone tell me, because sometimes I should go out to the left. If I go out to the left, out here, anyone tell me what the next critical number would have been out here?
Negative 5.
Oh, wow. Mathematicians in here. And it looks like I might have what, another asymptote here? Like this. And it looks like if I connect, I may have another piece that looks like that. Is that true? Woo! The reason I said we lucked out here, and they always ask us to draw usually 1 cycle, some instructors ask us to draw 2 cycles. How many cycles do you think we have here? We have 3. And usually I just ask for 1. So we're going to decide which one are we going to accept. Over here, we had to come up with one over here, and 2 branches, but 1 cycle. This thing, the way it came out, tangent, it has 3 complete cycles already. So on the exam on, let's see, it's going to be on Friday. Let's see if this is covered on Friday. You'll see the review. I think it is. Okay. You'll say, Professor, which one of those can give me a tan graph to work with? Which one of those cycles should I work with? And I'm going to choose one for you for a reason. I'm going to choose this one. It's called between negative pi over 2 and positive pi over 2. The others work, don't get me wrong, but I'm choosing of those cycles, the one I want you to remember for a reason is this guy. Caught between negative pi over 2 and a positive pi over 2. And that's going to be the parent graph. We'll accept that as my parent graph. This is the parent graph for C. This is the parent graph for tangent. And you saw the parent graph for sine and cosine last week. And cosine. Let me get some information from you. If I accept this, guys, I'll erase some of it. Can anyone tell me the domain, to be careful, I've got some clever students in the class. I see, there's some places there where X cannot be something.
Just listen.
X cannot be, and are you telling me maybe I could write it the same way I wrote this one?
Yes.
To pick up where those asymptotes were? Are you telling me what, pi over two plus? Right. Plus what, how do we write this? Pi k?
K is
K is an element of, straight, look at E there, the integers, and we know what the integers are. Nice numbers to plug in there. Okay, if I replace k by 0, that second term drops out and leaves me pi over 2. Was there sure enough at pi over 2 an asymptote? Undefined. If I try 1, replace k by 1, I get what? Pi. Pi plus pi over 2 is what? 3 pi over 2? I know I erased it. Was there an asymptote remind me at 3 pi over 2? I think there was. If I put a negative 1 in there, which I can, negative 1 is an integer, no fractions, no decimals. Put a negative 1 there, get negative pi. Now what's pi over 2 plus a negative pi?
negative.
Negative pi over 2, asymptote. So that little formula he gave me earlier, thank you so much. That's also what it looks like for tangent. Domain, range, we looked out here for range. The up and down. It's negative infinity to positive infinity. Period, gotta be careful. Joseph, I'm ready for you. Tell the class how to find the period based on about one cycle of this.
Well, it's pi, but.
The period is gonna be pi, but tell the students how it's pi. What do you think?
Negative pi.
It stops at pi over 2, right? My cycle stops at pi over 2. I would subtract from that, this is what it's gonna tell me. Where did it start? Negative pi over 2. I would find that distance between those, the beginning and the end. That'll tell me the size of the period, where the graph starts and where it ends. If I do this, I think I end up with 2 pi over 2, like fractions. 2's cancel, there's the pi. So every pi length, things will repeat. Now, before I leave that, pi over 2 right there has an asymptote. If I add this period number to it, pi over 2 plus pi, I think gives me what, 3 pi over 2? Was there sure enough another asymptote at 3 pi over 2? So just add the period and make things repeat. Amplitude, none. There is no highest number here to work with. Got to step back and look at period, domain, range. I am so pleased all the graphs are done except for cotangent. I'm leaving that one up to you. Guys, any concerns here? Now, PK, here's my concern. Whew, you know what they're going to do, close down chapter 5. They're going to say, take one of these, secant, could be tangent, could be sine, could be cosine, take one of those, place on the grid the parent graph, and then guess what they're going to actually do with it? Perform transformations on it. Now you talking about craziness? You take a graph like this, and they ask you, look at this, we're not going to do this now. What do they ask you to do this? Good luck. Now, could we do it? Yes. Would it take me maybe as an instructor probably half an hour? If I was careful and thought different colors and so forth. I got a little shortcut. I'll show you how to get to the graph, final graph, pretty quickly without going through all those transformations. Guys, if they ask you to do it though, this says reflect through the x-axis. You gotta take this and reflect it through the x-axis. Does that mean this piece now is down here? And this piece is up here? Oh, that's that down. Then you say, well, professor, what's going on inside? Someone remind me of what's going on inside. Yeah, first you're gonna rewrite it. The x should come first. And then tell me even more that we saw earlier on some other graphs. What else should I do? shift yet?
Move the negative.
Yeah, you're gonna factor that negative out.
Reflection.
Good, thank you. Now what picked up, this reflection to the x-axis. Good luck. Now this says now do what? Reflect it to the y-axis. And you're reflecting these. Through the x and also through the y, you're here now. And then if that's not bad enough, do what? A horizontal shift to the right.
Yeah.
Pi over 4, good luck. And then finally finish up PK, vertically shift everything up 5. That would be your final exam. That one question. You walk in and say, Rachel, where's your final? This is one page. How long is it gonna take you? 3 hours. On that one problem, 3 hours. That should be all those transformations. Gee, we'll be here all day. I'm gonna come up with a little technique to show you how to get to the, you're gonna be amazed, how to get to the final graph and not go through all those transformations on these trig functions. Guys, we'll leave that. You have only cotangent, I think it is, for your responsibility, to graph. Let's move into part 2. Now, before I give you the shortcut, and then give you a handout, and we'll start graphing some of these, where they look like we may have to go through transformations. Let me do this first though, because I got an accelerated class. If you were asked to sketch this, before I give you the shortcut, let's call it y equals this. Step back and look at it. Okay. I chose cosine. We're gonna do it. And by the way, this one has maybe 2 transformations. Okay. Oh no, it's in good shape. It has only 1 transformation.
Yes.
What's my 1 transformation?
Shift.
Shift where?
Horizontal to the right.
Let's look at that. Horizontally to the right, how much?
Y over 2.
So I need to take the cosine graph and shift it over, and I need let's see what happens. A conclusion. And I'm gonna do this first. I'll give you this shortcut of how to do things like this. Guys, first though, you need the parent graph. Transformations. Let's place the parent graph on here. Some of you guys should be the top students in those calc classes. Definitely. Okay, guys, cosine, remind me, I think cosine started here. 1, it drops down to the axis at pi to 2, down to a -1 at pi, back to the axis, back up to 1. The graph looks something like this. We saw that earlier, I think. Now, 1 transformation. Shift that red graph pi over 2, as he gave me, to the right. Now, I'm standing right here on the top of the board. I gotta be cautious myself. Guys, here goes. This 0 is not gonna be shifted to the right, pi over 2. Does that mean now, help me out, is this point right here now here? If I go pi over 2 to the right, we mess up here. This point, which is at pi over 2, which is 0, is now being what? Shifted pi over 2 to the right. Is it going to now land here? Yes or no? Don't mess up. This point down here is when we shifted over pi over 2. Now I'm at pi right now. If I shifted over pi over 2, where am I now? Is that right there now? Shifting things over. Where am I? I'm lost already.
2 pi now.
Are we at 3 pi over 2?
There it is.
Then shift it over what? Pi over 2 to the right. I'm at 2 pi now. Where am I now? Here? Help me out. Yes or no?
Yes, yes.
Now, I'm at the end, 2 pi, that's gotta be shifted also, doesn't it? And where's that gonna go if I shift 2 pi?
Awesome.
pi over 2 to the right, from here gives me what? Pi over 2. I'm at 5 pi over 2. PK, what should be happening there is that is now happening here. Is that correct? Is it true or not? Or what happened? Or did we stop here?
Distribute on the one.
Ah, are you saying right here, Professor, it's up here at 1?
Yes.
Was this over here, up at 1, where was I? Yes, up here? Am I at 1? Put that in the color here we need. Now, PK, see where you are. When I connect those, does it look like connected? It might do something like this. And I was careful, I was on top of the board there. Does that, I guess, purple graph, does that look like it's to the right of the red one? And I think we were described as what? It's horizontally shifted to the right. So does it sure enough look like the purple graph is to the, at least to the right of the red? And I hope we have all the points correct. You guys agree? Now, I need a clever student to answer the next question. And watch what is going to come up as a conclusion. Woo! Hang on. Ooh, I think I heard someone say something. You mean that purple graph? She's away from us, so that purple graph is the sine graph. It is?
Yes.
Selena? If it is, oh my goodness, I've been waiting for that response from this message. So are you telling me, let me graph quickly the parent graph for sine. She thinks that purple graph is the sine graph. If I graph it, the parent graph for sine, I'll do it in purple here. I think sine started here when we actually graphed it, did it? And did it not go up like this and connect and then make that wave? So actually, does that purple graph represent, as she tells me, sine? Here's what you concluded here. Selena, you help the class out. This is equal to sine theta. And pretty soon, hopefully today, you'll see an algebra way to do this, to show that that's equal to sine. Not just by the graph, but algebraically. Show it, it's equal to sine. Selena, thank you, that's exactly what I'm wanting to hear. Okay, guys, let's try something over. And then we're gonna close this down pretty soon. I think it's time for a handout. Someone remind me, the last handout I gave you guys, Lena, you're close by. Can you find the last one and see if I had any graphing on it or not? Was there anything on there about graphing? And so I'll get that out of the way because I have another handout that does have. Does it have anything on that about graphing? Oh, no, it does not. Okay, so we're ready. Here we go. Selena, not that response there. I want to hear. There you go. Guys, please stick around. These handouts help you. Because FedEx, I'm gonna make my copy. I'm busy. Did you get your exam back? Parker, you need a copy, Jim?
Sure.
Oh, you got one? Oh. Okay, PK, you're close by. The slide I look here, it says, I guess, definitions. Then all of a sudden, I think at the bottom there is where we start the graphing. Oh, I wonder why Ramsey all of a sudden is going to give me some type of a definition at the top there before I jump into the graphing. And I'm trying to get into this shortcut that where you could actually have a lengthy transformation problem done in no time. But I gotta lead you into it. Okay. PK, what did I start out with there? And the definition was, the function is even. And the definitions?
A function is even if for every act in its domain, the number of negative acts is also in the domain.
Okay, here we go. And did I finally conclude that f of a negative x, if I did,
Or,
equals f of x? Okay, here we go. This. Gotta do it first, guys. So if my function satisfies that condition, not only do we call it a function, we call it an even function. And it does something unusual for us, but it's an even function. Guys, before I jump in, I don't know whether I give examples or not. Can anyone give me a basic for middle school, a function that you might consider even by this definition? One of the most basic functions out there that would satisfy this condition. No, I want a basic middle school. It would satisfy this, and it's a function, but we will call it an even function if it will satisfy that definition. Someone recall what maybe it looks like?
X squared.
X squared. Most basic. Okay, under here, this, f of x is equal to x squared, middle school. Now, put a semicolon here. Why can I classify this not only as a function, but an even function? Watch what happened. I'm gonna take f of a negative x. Watch what happened again. F of a negative x, let's go back to my function. Replace x with a negative x, and square it. And if I do, of course, we'll end up with x squared. Please tell me, was that the original function I started out with? So when I replace x by a negative x, do my business there, takes me right back to where I started, that's what this says. So if you think of a function that does that, it's an even function. Just out of curiosity, does anyone else think they may know one from middle school before I show you the trig functions that might be considered even, besides x squared? And we'll test it. Yes?
Absolute value.
Look at this. So you're saying, Professor, f of x equals absolute value of x. Like that. And you're telling me now if I try this definition, f of a negative x, to go inside there and replace x with a negative x in his function. Guys, can I go ahead and call that just this? Are they equivalent? So does it take me back to the original? So if you have a function that you replace x with a negative x throughout, simplify it and it takes you back to where you started, it's an even function. Now, with that said, I'd like to now identify which of the 6 trig functions can be considered even, because it's going to play a part in graphing here shortly. Now I've got 6. Sine, cosine, tangent, secant, cosecant, cotangent. I'd like to know, based on some reasoning, which of those, if any, can be considered even. Okay, come again, I heard something. Okay, try cosine. Arena, hang on. She says, Professor, try cosine. Cosine x. Now here's, I need a rationale. She says she thinks that's even. I'm going to agree with her. Cosine's an even function. You say, Professor, it's not as easily done as this. I can see quickly replace x with a negative x up here, this x squared, and it takes you right back to where you started. Are you telling me, Arena, if I replace x with a negative x here, let's set a bone here first. We're saying take f of a negative x in cosine, it looks like this if I do it, cosine negative x. Arena, are you telling me it takes me right back to where I started? If it does, it's even. Replace x with a negative x, does it take me right back to where I started? Arena, I'm gonna agree with you, it does. I don't know how we are going to show it does. You have any ideas how to show it?
I remember something about like the circle, on the circle.
You mean the unit circle? Hang on a second. I'm not gonna draw the complete unit circle. I'm gonna do this much, Arena. I think what you're thinking there is gonna help me. Just on the side here. Let me do this and ask you a question here. Suppose I, in quadrant 1, sketch an angle. And it looks like this. Quadrant 1, just a basic sketch of an angle. Line this up. And it looks like that. And I'm gonna name it as theta. Now, this says something with a negative theta. Can anyone tell me if I sketch the same size angle, but now take into consideration the negative sign, where is that angle located? Do you think? Theta's in quadrant 1. Where location would that negative theta or negative x angle fall? Fourth quadrant. Thank you. Moving, what do you call it? Clockwise? Sure, down here. Hang on, try to make it look as reasonable as I can. You're there. And I do want it to have the same size as the first one. Okay? Now if you'll put a negative sign there just to show negative theta, go for it. Same size angles though. Now suppose I ask you cosine of theta in quadrant 1, and cosine by definition is x. What is it? Is it positive or negative? Positive. Now suppose I move down to quadrant 4 and ask you what's the cosine of a negative theta. And you're in quadrant 4 and cosine's definition is x. What's x down in quadrant 4? Positive. Is cosine still positive in quadrant 4? Does it make an agreement? They're the same. So I can identify cosine as an even function. That's going to play a big part here. So this is even. Rita, you said it was. I'll accept it. There's a little rationale why. These right here will give you the same value. Cosine's positive here. Cosine's positive here. Of course, I have the same size angle. Now, cosine. If cosine's even, what other of the 5 remaining ones might also be even? That's related to it. Secant. Throw this in. Without a rationale here, number 4. F of x is equal to secant x. Also, if I need it, is even. Now, I will tell you this much. Cosine and secant even. The other 4, we're not going to test all of them. The other 4 are odd. Now, they have the definition on the handout for what an odd function is. The other remaining 4 will be odd functions. But we gotta see why. Nice, nice, nice. Then we're gonna do some graphing here. Get this done. Okay. Read the definition for odd function.
Mention it's odd if for every number acts in its domain. The number negative x is also in the domain, and f of negative x equal to negative f of x.
Thank you. This time they're not the same. They are opposites of one another. And that's what an odd function is by definition. First, before I jump into the tree and show you the other 4 are supposed to be odd, we'll test a few of them, show they are odd. Can anyone tell me from middle school? You guys gave me this from middle school for an even. Anyone give me one from middle school that if I check it by this definition, it becomes an odd function, not just function, an odd function. What do you think?
F of X equals X.
Oh, wow, I thought, okay. Hang on. And then I do this to what he suggested. PK says, Professor, then would you take f of a negative x? If I go to his answer, I'm gonna replace x with a negative x, it looks like that. And now, is that the opposite, look at this, of the original function that was given? And the original function was x. So is this result here the opposite of the original? If it is, I'll take that. So x, just x itself, is considered an odd function. Now, give me another one before we jump into the tree. X cubed. Absolutely. Let's test it right quickly. And PK says we're supposed to do this, take f of the negative x. I will. Now on Arena, to find f of a negative x on your function, it says replace x with a negative x, which I did, and cube it. If I cube it, I get this. Now, is that answer right there the opposite of what she gave me originally? Is it true after I did the work there? Is that the opposite of what she originally gave me? If it's the opposite, it's an odd function. Okay, so x cubed, x to the fifth, x to the seventh, all those. Yeah, Professor, the trig functions, which ones are odd? There were three of them, pick up this one. First, tangent x. The one that's staring at me right here. Tan x. I'm gonna test it here, here goes. Let's find f of a negative x. That's what the definition says to do, which in this case says go to tangent and replace that x with a negative x. And you're supposed to try to show you get the opposite of what you started out with. You're supposed to get negative tan x. If not, something's wrong. So guys, that's what we're supposed to get, the opposite of what you started out with. Can anyone in the purple there convince someone that this, when you discuss it, will give you that? Rena?
Sine x is odd function, so when we're dividing sines over cosinus, it's gonna be.
Now, you know sine is odd, cosine is even.
Yeah.
So you put sine over cosine, which is tangent, 100%. So you're placing an odd function over an even function.
And if we will replace sine x over, by sine minus x, it's gonna get minus tangent.
I follow your reasoning, no problem there. If I go back to the sketch here, which I think you and I are going to be saying the same thing. Look at the sketch here, guys. You've got theta in quadrant 1, then negative theta, since they are mentioning a negative here. Negative theta would be down in quadrant 4. What's tangent y over x if you're up in quadrant 1? Positive. What is negative theta, which is in quadrant 4? If you're in quadrant 4, you're placing y over x for tangent, you end up what type of result? Are they the opposites of one another? That's exactly what we want. We'll show this is the opposite. Does it make sense, guys, the way we did it? Quadrant 1's positive for tangent, quadrant 4 it's negative.
Yes.
So they are opposites of one another, which I think, PK, you're telling me that's what I'm supposed to end up with. The opposite of what you started out with. So guys, tan is considered an odd function. I will tell you without any more discussion, the other three remaining ones are also odd. The only two even are secant and cosine. You say, Professor, how's that going to help me? What's it going to do for me, Professor? That makes a little sense here. How's it going to help me? Here we go. PK, you're close by. Did I on that handout now jump into maybe asking for a sketch?
Yeah.
Oh, wow. Hang on. Leave that over there. And what was it, PK? Read that to me. I'm asked to sketch what?
F of x equal
Cosecant or cosine?
Cosine,
Cosine,
pi over 3 minus 2x.
Like that. Beautiful. And they want you to graph that.
Transformation.
They want you, yeah. Now, hold on, if you want to do it through transformations, and I'm gonna insist or give you which, method to use, you can use transformations. Guys, first though, if you were gonna go through transformations, inside here should be simplified. We all know that, that X term should come first, we've done that before. So turn this around. We gotta be a little careful here. And then what else might you suggest inside there in that purple?
Take
Should we even simplify further, take out what?
minus,
Minus, in fact, minus what?
minus 2.
Minus 2, like a common factor. Be careful. Please tell me, I'm on top of the board here. Is this equivalent to negative 2x plus pi over 3? If you multiply this out by the distributive property. Negative 2x plus pi over 3, is it?
Yeah.
Okay.
It's another angle also. It's 30.
But is that equivalent?
Yes.
Now, if we're gonna do it through transformations, which we could, here we go. With what she gave you, you have to show a reflection through the x-axis. A reflection of what, Professor? The cosine graph, the parent graph, which I don't have up here yet. Reflected through the x-axis, then what would this do? What effect?
Times 3 is a wideness.
Well, it's gonna vertically stretch it
Yes.
by a factor of 3. We can do it, takes a little time. Then all of a sudden you jump inside the purple, you're not finished. I see another transformation thing. Here's 2 already. The third transformation,
Minus 2.
reflect through the
Horizontal.
y-axis. As if that's not enough, now 2. Anyone tell me what you think the 2, what effect does the 2 have?
Horizontal stretch.
A horizontal stretch or shrink my graph.
Yeah, negative.
And as if that's not enough, that. Which says at the end, do what now after all this other stuff's going on? Horizontally shifted what?
To right.
5 or 6 to the right. Good luck. You talk about colored pencils and so forth and so on, you'd be looking for colored pencils. To keep straight with what's going on here. Let me count here, guys. I got 1, 2, 3, 4, 5 transformations, and along with the parent graph. You've got 6 graphs on one grid. If I count those correctly. Now you go to a calc class, and your calculus instructor says we're going to do a calculus procedure on cosine. And you'll shake your head, okay, I sort of remember Ramsey shows what cosine looks like. And then we'll say, okay, let's do this calculus procedure. And all of a sudden you're going to say, oh, and they may say, we could sketch it. And then we'll do the calculus. They're waiting for the calculus from you guys on this. You say, oh, I'm gonna sketch it by doing that and that. Reflect through the y-axis. Stretch by a factor of 2. Shift it to the right, 5 or 6. And the instructor's gonna say, no, no, no. You gotta do it quick because I'm gonna ask you to do some calculus on it. Then I'm gonna ask you to wait 10 minutes or 15 minutes to sketch it. They don't want that, they want you to just quickly do it and then do some calculus on it. We're interested in the calculus on this, okay? June, Mr. Parker, I don't know how much you guys in your calc courses, did you guys actually have to take a derivative or something like this of a trig function that might be a little involved? See your head shaking.
When we would replace x by something.
Now, did that instructor wait for you to go through 7 steps to sketch the graph? I doubt it. Did they? They didn't ask you to go through 7 steps or whatever, all these transformations, see? No, wait, we did transformations and it's beautiful, but sometimes you don't have time. So Professor, what are you gonna do? Okay, here we go, guys. Let me rewrite first what we have. We have negative 3 cosine. We have a negative sign inside there, 2. X subtract 5 or 6. That's what we have, if I didn't copy something down. To work with. My graph, it's gotta look like its parent, cosine. I did the cosine graph, I think, earlier today. So I'm gonna simple that. And I gotta do it fairly quickly, and here's what I suggest. First, we gotta simplify this a little bit. You say, Professor, I love it, what's simplified? Look at this. Cosine has been identified as, where am I? Was cosine identified as an even function?
Yes.
You see now why I did these definitions. What can I do with this problem right here quickly and at least help myself out, knowing that cosine is even? Tell me what might happen.
You can get rid of that negative in front of the 3.
So that's one transformation gone. Just knowing it's even. You're allowed to drop that negative sign. That's exactly what I want to hear, guys, here when we discuss this. Oh, it goes on here. The negative sign disappears. If you have cosine negative x, is that true? So that's one transformation that you would not have to worry about. And I said, Professor, what else are you going to do? Well, it's in pretty good shape here. What I'm going to do now is, here goes, I'm going to take this piece here. We're not going to do it through transformations. I'm going to bound this, use that word. I call it the argument. Inside there it's called the argument. We're going to bound that argument the way we bounded the parent cosine graph. Anyone tell me, I just did it today, where did the parent cosine graph start and where did it end for one cycle? On the x-axis, where did it start and where did it end? I want this one to do the same.
Pi over two to 5 pi over 2?
No, I don't think the parent graph for cosine, no, the parent graph.
0 to 2.
I think we started at 0 and went out to where? 2 pi. I want this one to do the same thing. So in other words, I'm gonna do this. Watch carefully. I'm gonna place 0. I want the argument, look at this, unusual, to be bounded, written like this, between 0 and 2 pi. Because my parent cosine graph was bounded that way. You guys are right, these came from the cosine graph. So I want that argument caught between. Everyone with the rationale so far? Now solve for x. Or solve for theta or x in this case. Guys, divide everything by 2. Like this. Divide everything by 2. And then solve for x. Next step to solve for x, merely do what? Add pi over 6. Pi over 6. Pi over 6. I solve this inequality. These two drop out, which I wanted. That leaves x in the middle. Pi over 6 over here. That's not equal to. That's not equal to. Guys, these two put together, we give you what? With a common denominator of 6. 7 pi? 7 pi over 6. Now, did anyone tell me in this class, what have I just discovered about the graph of this function as I get to the grid? What do you think I've just discovered?
In which quarter?
Again?
In which quarter?
No, something better, something better. Give me a description. Wonder what this business just gave me about my graph.
Fine.
Sort of domain's tied in, something else.
Name of the period.
Period, I'll take that also into consideration, something else. Which is going to be so helpful.
Can you,
Yes.
The starting point? or-
Yes, it's gonna start at pi over 6. And guess where it's gonna end? 7 pi over 6. My cycle, but I don't have it drawn yet, but it's gonna start at pi over 6 and go over to 7 pi over 6. But please, guys, remind me, this is a cosine. On the side here, real quickly. Do it as quick as I can. Remind you what that cosine graph looked like. You guys can help me out here. Real quickly. I think it started up here, up down, right here, back up, back up to 1, and we saw that earlier. Now, what we've discovered is my parent graph started at 0. This graph is going to start at pi over 6. My parent graph ended at 2 pi. This one's going to end at 7 pi over 6. So I got the beginning and the end. Someone described that perfectly. The beginning and the end. Are there, even on the parent graph, are there some angles caught between them? The beginning and the end, we know that for sure right now. Are there some angles also caught between? How many angles are caught between? How many angles are caught between the beginning and the end of the cycle? Here's the beginning. Here's the end. How many angles are caught between?
3.
3.